some teacher who is having some say other issues. So my class will be mainly covered on the second part of the syllabus. If you look at the syllabus in your website, so second part means actually it is that PLC control of electric drives, or then control of electric drives in terms of braking, and then speed control with the help of microcontrollers, those things. But before that, we should be learning regarding the basic methodologies. Maybe you have read in your second year or third year classes, but still here the application part, actually how will we able to implement it in practice, and what are the pros and cons, etc., etc. It would be much better if we have had physical classes. There we could have shown a little more on the board or to other cases. Now, is it I mean, the screen is available to you?
Yes, sir.
Screen?
Yes, sir.
Now, unfortunately, I cannot go to the presentation mode, but I am, because of the licensing issues and all, I am facing with my laptop. So, I have just enlarged the slides. Okay, probably this will help you a little bit. Now, this, you see, these are the way I will present here. It is mainly my handwritten things, taking photographs, what I would have written on the board. So this thing, and I will be supplying you the same thing to you. Maybe everything is not written, but some reference books also I will tell you afterwards. But before that, we should start with the basic things of drives. So this is what topic it is written: microcontroller, DSP, and PLC applications to motor drives. So this is the main topic which will be covered in this. Now motor drives is a very vast thing. We will segregate this thing to starting, braking, and then speed control. Okay. So now, if you look at a drive system, so what is a drive system by definition? Why do you need a drive system at all? You have power supply, you have motor, right? If you connect the power supply to the motor is going to run. But why do you need a drive system, and what does it do exactly? Are you having any idea about it? I think last semester your electric drives course was there, is it? Or now next? I think last semester electric drives course was there. No, it was there, nah? So I think I was also one of the persons taking the classes, maybe, huh? So so then you tell us, what is a drive system actually? Why do we require a drive system at all?
For control purpose.
Well,
For
see,
speed
you will
control.
be facing interviews. I'm telling you one truth. Those, I don't know in this situation how many core companies are coming, but in future many of you will be trying to join core companies. Now, if you see the formation of this industrial system in our country, or even in say outside India, Europe, or America, wherever, USA. Now you will find that the core sector mainly actually consists of few things, like few sectors, you can say. One is majority is a steel sector, right? Another is a power generating sector. Now another will be the process control, like say chemical plant process control, like say this Reliance and all. And few of them will be actually manufacturing those say machines and drive systems, so like Siemens, or say earlier it was Allen Bradley. Now it is I think name I'm forgotten. Allen Bradley, Rockwell Automation. So Rockwell Automation, Siemens, ABB. So these are system providers along with the motors and drives. So these are the sectors. Okay. So now all these sectors, they are serving certain loads. Core sector I'm talking about. Load, or you can say they are designed for some loads. Say electrical generation you have, and then there are certain loads. Now generating unit and load unit, and in between say transmission and then distribution unit. This constitutes the total your electrical thing. Now you see, when you generate electricity, you find that till now, of course, nowadays that PV sectors like say photovoltaic generations and all are coming, but except those, 95% of the generation is made through electrical machine, right? Electrical machine. Now maybe it is a synchronous generator or alternator, maybe it's an induction generator, or maybe it's a DC generator or some other form, right? Say brushless DC generator, or you can say switch reluctance motor generator. Many applications are there for non-conventional, even conventional. So 95% of power is generated through rotating machines, right? Now if you look at the load sectors in the core engineering, load, what are the loads? Now when you see those steel plants, process industries, power plants, etc., you will find that that 80% of the load what we have in the total universe, you can say 80% roughly, those are motor loads. Those are motor loads. Now rest 20%, now roughly speaking, 10% is lighting load, and another 10% is say heating and other say typical type of loads, specific type of loads. Now 80% are motor loads, right? And again, out of which 80% motor loads, you will find that 90%, or even say a little bit less, 85% to 90% of the motors are induction motors. So now, what will be the, just a minute, some phone call. Hello? Huh? Huh? Oh, already you are having a class. Huh? 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 Friday 12 to 1. Okay, Friday 12 to 1 is possible. Okay. Okay. For this week only, you make it Friday 12 to 1, and next week only we'll be back to the normal schedule of Thursday. Okay. Okay. Thursday there is a problem. Okay. Let us take it on Friday, and then we'll decide on the final date. Okay. Okay. All right. Yeah. So, তোমরা শুনতে পাচ্ছ তো আমি যেটা বলছি?
Yes, sir.
হ্যাঁ স্যার
So now you see that, so there you see motor loads I'm talking about. Now these motors are connected to different types of loads, right? Maybe it's a CR, maybe it's a pump, maybe it's a say normal say rolling mill rollers. In industries or even in your home, you find that loads are either in refrigerator or in fans or in say air conditioners. Now here I am telling you, in the summer time, do not run those say refrigerating system or fans too much. Sorry, in the winter time. In the winter time, when you do not run the refrigerator system, like say AC or fans too much, you will find in your home also the electric bill reduces to around 1/3. Just rough figure I'm telling, because the fans and this refrigeration cycles are lesser, right? And in the summertime, the bill is at least around 3 to 4 times compared to. Then you see 75%, 60 to 75% of the loading is taken by motors. A rough idea. Now, if you go to industries, the ratio will increase. motor load will be little more. So I'm talking about 80 to 85% of the, so 80% of the loads are motor loads. Okay. So then there's a non-example. So now when they are fitted to different kinds of loads, now if we directly connect the motor to the source, now the motor will take the power as per the source power. I mean, if the source you assume as infinite, source of infinite power, and the motor will take its own power and run. Okay. Now when there is a question of say meeting the load means say we want the motor to run at a specific speed, delivering a specific torque, right? So then that question will be overturned. Okay, because motor is normally taking the source as a supply and then running its own as per rated power if the source is rated value, right? So then the question of the matching the load characteristics doesn't arise. So we do not want, like say a simple example in your home also. Say you don't want the fan to run at same speed all the time. So whenever there is a little bit say drop in temperature, so what you do, you try to adjust the speed, right? That means you don't need that much of air. So naturally there must be some conditioning unit in between to control the flow of power from the source to the motor so as meet the load. So that is what a drive system is. That means when a motor is connected to the load, a via media, you can say a via media device is there, which will control the input power to the motor so that the load characteristics, or I mean the idea to operate the machine at different loading points can be achieved. So it's mainly a conditioning unit, power conditioning unit. So that is what is shown here in a drive system diagram. You see that this is a source in the left side. Now we have a power modulator, which is actually a drive system. Now a drive system normally people define in various ways. Many of the literatures you will find that they are defining drive system along with the motor, power modulator, and the control unit and the sensing unit. Okay, the total things. Now you see here the source is supplying power to the power modulator, and this modulator has an output power to the motor based on the load demand, you can say. Now in order to control the motor, so there may be different you can say different parameters you need to visualize, or you need to have as a feedback, right? So one of them could be the speeds, could be the motor currents, could be the voltages, other things may be also there depending on the type of control. So we have sensing units. So sensing units are symbolically shown between motor and the load. So it can have even before the motor, because if you want to sense the current supplied to the motor, that then arrow should be here also. Okay, so it's a symbolic. Now there are sensing units to sense different variables that are to be controlled for the motor side, and then the sensing units give some feedback to the control unit, and control unit decides that how the power modulator should operate to provide the power which will match the load. And in the bottom we have input command. So input command could be your say speed reference, could be your torque reference, whatever it is, depending on the mode of control. So this is the diagram of an entire drive system. Okay, so is it clear? বুঝতে পেরেছো ব্যাপারটা? ড্রাইভ জিনিস কেন কাজে লাগে, তাতে কি থাকবে?
Yes, sir.
Now this power modulator, you see that control unit will actually try to control with the help of some pulses. Now the power modulator will mainly consist of different power electronic switches. Okay, so the switching pulses will be provided from the control unit so that appropriate voltage or appropriate power is fed to the motor. So that is what this block diagram. Now we will start with starting application. Say starters, right? So PLC application, say DC motor starter, DC drive, DC motor starter. So you know what is a starter for a DC motor? What is a starter? Can you just elaborate on this a little bit? What is a starter? Huh. Right. It is absolutely right. The thing is that, say, when you see that DC machine or a DC drive system, now we have impressed voltage, and then the output is either speed or torque, right? And it takes current. So torque is, you see that K phi Ia. That means if you assume that the field flux remaining constant, so torque will depend on the motor current, right? So now you see that that EMF equation for the DC motor is written here after having applied the KVL in the loop. So you will find that V is actually back EMF plus IA into RA. So back EMF is nothing but K phi into omega. Omega is the rotational speed of the machine in rad per second. So phi is your flux and K is the machine constant. Now from here you get that the current expression is given by V minus K phi omega by RA. So under normal running situation, you see that the difference between V and EB is very less, okay, of the order of few volts. And if your RA is of the order of say less than 1 ohm and few volts divided by less than 1 ohm, say around, depending, RA will depend on the motor rating, of course. So you get a current which can be within the limit of the rated current of the machine. The the situation differs when you start the machine. So as soon as you start the machine, you see that omega is 0. This right hand side omega is 0 because you are starting it. Normal running omega is there. So when you start it, omega is 0. So the current at starting is given by V by RA. So now if you have applied rated voltage here, and RA I am talking is always less, always less. Even for a 1 kilowatt machine, it is about 0.5, 0.6 ohm. And if the rating increases, it becomes lower and lower, right? So naturally, if it is a 220 volt machine and RA is 0.5, so a current of 440 ampere will be there at the time of starting. So which is undesirable, which can do many damages, like it can damage the armature or the brushes, or even it will have a very huge torque at the time of starting because IA is very high, flux is kept constant and rated value. Now torque is very high, and the motor will try to accelerate at a very fast rate, which can damage the bearings, other things. So all these things disallows that we can just have a direct voltage application to the DC machine. So now what is done exactly? Now, actually, this is what is done. This is what I was trying to explain here in the next page. Omega equal to 0, this IA will increase like that. So what is done exactly? That we need to have some external resistance in series with the armature to limit the starting current to a value which is actually tolerable by the motor, as well as which the torque which is generated, which is actually also tolerable by the bearings, right? So this external resistance is a must during starting because we don't have any other option in earlier days. Because the other option could be you can apply a reduced voltage at the time of start, right? That's just what you do in your lab classes for induction machines, isn't it? Induction machines, what do? You have a variac. Variac, you just increase the voltage from a small value to high value so that the starting current is limited. But here, a variac operation is not possible because it is not an AC source, it's a DC source. And at the same time, other things that can be possible is a DC potentiometer. But the size of the potentiometer will be very large because it has to carry the load current, right? So these are infeasible actions, right? So therefore, actually, the only option is to have some external resistance in series with the armature, so that to limit the starting current to a desirable value. Maybe you want the starting current to be, say, 150% of full load current, because this does not remain for too much of time. The speed is 0, it is 150%. As the speed is increasing, naturally your current will get reduced. So therefore, you don't need that initial resistance to be always in such a way that it is only 100% of the rated value, of the allowing 100% rated current. Okay. So you can have a choice, like say 150%, 125%, like that. So accordingly, you have to design our external, right? Now, there are other things also. Now, supposing this thing, actually I did not write, or other could not write. So how much I will write? So the other thing is that, supposing you have started the machine with the help of this external resistance, right? Let us say you have started it. So now what is going to happen after starting? So during starting, it is all right. So you have a resistance, and that reduces the starting current. Now, after it has started, then what is going to happen? Now, if this resistance remains in the circuit, you will see from the previous equation, omega here is actually V minus IARA by KFI, right? So KFI is your rated value, right? Now, IA is initially high, then it will slowly reduce to a value of say rated current or something like that, slightly lower than the rated current. Now during starting, if you have some external resistance, so the equation will be not only RA, it will be IA into RA plus R external. So then omega is nothing but V minus IA into RA plus R external by KFI. So naturally, if R external is high, so the speed will be lower than the expected values. So the motor will settle to a speed, if the resistance is remaining in the circuit, to a speed which is much lower than the expected value of the rated value. So this is not desirable. You want lowering of current during starting. At the same time, you want that the motor speed to reach its value or the desired value. And moreover, this resistance is carrying the armature current. Therefore, there will be huge amount of copper losses in the circuit, right? Because I square R external loss. So these things actually, this allows the retainment of this R external in the circuit during operation. So somehow you have to remove this R external after the motor has started. So you can have an option. You can have a simple option like that. You can have a parallel switch, right? Parallel switch. The switch is off during starting, and when the motor speed has reached, you just turn on the switch so that there will be a short circuit across this R external. So current will be flowing through the short circuited path only, right? So again, this will give rise to certain increase in voltage across the armature, because see, keeping this R external means that we are applying lower voltage at the armature, because you see that voltage applied this across the armature is nothing but V supply minus IA into R external, right? Now when R external suddenly becomes 0, so this IA R external drop will be suddenly become 0, and the full voltage will be applied to the machine armature. So that is also not desirable. Now here IA Same thing I'm talking about. So VA is VT minus IA into RA plus R external. So IA is VT minus K phi by RA. So effect of sudden change in supply. So suddenly say R external is 0. So now your next IA is nothing but V minus K phi omega by RA. So let VT1 be the initial voltage and VT2 be the final voltage. So IA1 is nothing but VT1 minus E by RA. Right? VT1 minus E by RA. Initial voltage VT1 minus E by RA. And then IA2 is VT2 minus E by RA. Right? VT2 voltage has changed. Since E is K phi omega and omega cannot change instantaneously, during this operation, suddenly you are removing the distance. So like starting also, we can assume that it's a mechanical system. Suddenly your speed will not change. So, so therefore E will remain same in both cases. So now IA2 minus IA1 by IA1. So percentage change in IA, if you see, is VT2 minus VT1 by VT1 minus E. Right? Now delta IA by IA1 is delta V by delta E. VT1 minus E. Now the armature resistance drop is about 2-3% of VT, maximum 5%. That's what I was telling. That V minus E difference, right? V minus E difference is quite less, right? So then V1 minus E is nothing but 0.04 VT1, right? So now you see that if you put here delta IA by delta IA1 is if you put 0.05 in the bottom, you will find 20, right? 20 delta V by VT1. So thus a change of 1% in armature current, sorry, 1% in terminal voltage, 1%. So if delta V is only 1%, just a minute, someone is trying to join, is it? Right. দেখতে পাচ্ছ তো তার মানে ডেল্টা ভি যদি 1% হয় সো ডেল্টা আইএ will change 20%, right?
Sir.
20%, by mistake I wrote 5%, it will be 20% change in the armature current. আমি কি হচ্ছে হঠাৎ করে হ্যাঁ বলো
স্যার বলছি যে প্রথম যে সিচুয়েশনটা ওখানে VT1 যখন ভোল্টেজটা তখন তো আমরা এক্সটার্নাল রেজিস্ট্যান্সটা কানেক্ট করে রেখেছি, তাহলে তো IA1 ইকুয়াল টু VT1 মাইনাস ই বাই RA প্লাস R এক্সটার্নাল হবে না?
না না এখানে কিন্তু জাস্ট সিচুয়েশন দুটো দেখাচ্ছি যে হাউ ডেল্টা ভি অ্যাফেক্টস armature current. It has got no relation with I have an external resistance or not no external resistance. So this derivation is to show that suddenly if we change the voltage from VT1 to VT2, what will be the current? What will be the effect on armature current? Right?
Okay.
Got it? Having same value of RA.
Yes, sir.
So now the thing is that if we have from this, if we have only delta V of 1%, so current change will be 20%. That means এবারে যদি IR ড্রপটা নিয়ে এবার চিন্তা করো যে সাপোজিং IR external drop was say 25% or 30%, right? Now if this percent into 20, now it will be 600% change in voltage, right? Just a minute, again they are calling. Earlier hello, so what do then? Then you make it on Saturday. Okay, so then we'll talk. Now I'm taking a class of final year. So I will talk say tomorrow. Say at sometime at 3:30 or 4 o'clock, you phone me and tell me the final time. Okay. 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 So this is the situation. So supposing, so this is what I was talking, that a small change in voltage can give rise to very high change in armature current. Okay. So if your IARA drop, if your IAR external drop was high, say 50% of the voltage, let us say. So now 50% into 20, so 1000% means 10 times current will rise. So we cannot have a system which will just drop the resistance instantly after the machine has reached speed with the external resistance, right? So that is why you see, you have seen the starters in your say laboratories as well as in your third year classes also, DC motor starter design. So there are different segment resistances, right? These segments are designed in such a way that the current change is always limited within the specified value. Say maybe maximum current you allow up to 150%. So you design like that. So in your starters also, 4-point starters, 3-point starters, you have seen many starts, copper starts, and your handle was touching those starts one after another when the speeds was rising. Remember it? Do you remember it? মনে পড়ছে?
Yes, sir.
So these are the resistances. So R1, R2, R3, R4. I have shown only say 4 sets of resistance. It could be say 5, 6, whatever it is, depending on the design. So that is what it is written here. So the resistances are to be reduced gradually so that the current change is limited to within the retained current or the desirable current, whatever it is. So the current changing graph I have shown here. So supposing it was initially you have designed it such that it is 150%, and then it reduces to a value of IA2. That means actually maybe you allow up to say rated current or 80% of rated current, whatever it is for the design. Now you would change next one resistance. So you reduce this R1 here. Now current again will rise with the next of resistances to this value, and again it will reduce because the speed is increasing, right? So this way your current plot will be there. Okay. So now you see this C1, C0, C1, C2, C3, and C4. These are actually, you can say these are switches. Okay. So in case of automation or automatic controls, these will be the contacts of some contactors. So you have read what is a contactor, what is a relay, right? So these contactors can be switched on at the sequence, right? So initially the main contactor C0 will be on, right? So that your current flows through all the resistances R1, R2, R3, R4, and total sum of these 4 resistances will give you the R external value, which I was showing earlier, R external. Right. Now, after some time, when the current has reached IA2, C1 is switched on. What is going to happen? The current path will be through C0, R4, R3, R2, and through C1, not through R1, through C1, because there is a short circuit with R1. In the next slot, C2 will be on. So C1 and C2 will carry current, and then R3, R4. Next slot, C3 will be on. So C1, C2, C3 will carry current and through R4, and then all the contactors will be on. So in this way, you can design your switchings, and then you can start the machine with the help of automatic starter, right? So now, something I will tell you, the current plot actually, the speed plot. Sorry, the speed plot. This is the speed plot. So have you got this slide? Uh, Now see, after at the time of T1, the speed was at I1. Now the next speed is I2, sorry, omega 2, omega 3, omega 4, and if it is a fifth one, it will be omega 5, or it will be omega final, right? Omega final. So the speed plot against the current plot, so will be like this. This is the speed plot, and that earlier one was the current plot, right? This is the current plot. So just a minute, I have to switch on the light. So now this is written here at T0, right? At T0, just starting. C0 is on, C1, C2, C3, C4 is off. Now write this at T1. After that time, C0, C1 is on, C2, C3, C4 is off. In this sequence, you have to switch on, right? And current is always in between IA1 and IA2. So this is the basic operation of a starter. If you remember your earlier classes, and you have designed the values of resistances also depending on how many resistances and currents, alpha values and all. If you remember, you have done it. So if you have not, so you can go through your say third year syllabus of DC machine starting, right? It will be there. Okay. So this is what. So now, how to design a PLC-based automation, automatic startup, so that I start and it will do the functions like this. So now you have to develop certain logics and program it in your programmable logic controller. So I think basic introduction of programmable logic controllers has been given to you. Is it? জানো তো programmable logic controller PLC জানো তাই তো? It has got input modules, output modules, and input modules actually they are through field switches, and there are programs inside. That is the ladder logic. Normally we have. Nowadays, few of them are having function block programming and all, but normally ladder logic. Okay. Ladder logic, you have NO and NC contacts, and then timers, counters, analog inputs, analog outputs, everything, digital inputs, digital outputs, like that. So now, if you see here, implementation through say PLC or an automation devices can be done on many ends. First of all, you can have a time delay sequence, right? Time delay means what? What we were seeing here. Now, if you go back to this logic, now we are seeing that that at T1, the speed is saturating, and there we can actually switch on the first contactor. So you can have some estimation based on your practical experience. So then T1 can be 1 second or 1.5 second, T2 could be 1.2 second, then T3 could be say 1 second, 0.9 second, like that, right? So based on the time sequences, you can just switch on the contactors, right? So that is what first thing has been given here. So you have a start switch. Now start is an NO contact, so I have shown as a switch just to show you. You can replace it with the help of an NO contact, like say whatever is shown for C0. So this is start, and we can have a stop. Always stop should be there. NC contact, NC. So it will be like a cross, right? I think NC I have not shown anywhere. I'll show it later on probably. Okay, this is NC contact. This NC contact C2, right? So NC contact how to represent you should know. And then the first line, each line is known as rung, R-U-N-G, rung in a ladder logic. I think you remember it. Now the digital inputs are start, stop, right? Start, stop. These are the inputs, right? And then outputs will be actually the contactors. CO, C0, C1, C2, C3, C4, like that. Now when you press the start button, so the power from this will go through this line and go to C0. This is a plus line, this is a negative line, positive line, negative line. But in ladder, there is no positive, negative, but we always assume that the power flows from left line to right line. Okay. So then C0 is on. Now, when C0 is on, this is known as a latching contact below this, below the start point. Now C0 will be on this contact. Now the starts are actually push buttons. Okay, starts, stops, they are push button. Push button means you push it and it is operating, and you release it, there's a spring return, it will come back. I think many of you are having AC in your home, or even in the classes you have seen there are ACs. Now you see that that some red buttons and some green buttons are there. Okay, so the green buttons are start buttons. Normally we start it, and then if you release it, it comes back. So it comes back. So naturally, the power to C0 will be actually disrupted when it comes back. So this C0 contact below the start switch is known as a latching contact. So the power is continued through this C0 through stop, because it is an NC and flows to C0 as your start button is a spring return type. So now 0 is on, that means the motor has started with all the resistances in the circuit. Now when C0 is on, this C0 is also on, down in the second rung, you see this NO contact of C0 is on. Now there is another box in the right hand side. It is known as TDOE. This is a timer. TDOE means time delay on energization. It's an on delay timer. That means it will allow power to C1 after some time, which is a preset value. Maybe 10 seconds, maybe 60 seconds, maybe 90 seconds, like that. So you have accumulated values and preset values. So accumulated values is a real time value. It will increase second by second. As it equals the preset value, here it is 10 seconds. So naturally the power will be through to down C1. Now the contactor will be on, C1 contactor. So C1 is on now. Now when C1 is on, the below contactor is again on, again T2, TDOE, that time, different time also you can set. C2 will be on. So as a sequence, you can turn on up to C4. So that 0, C1, C2, C4, all are on after some time, and the machine is running at without any external resistance in the circuit. So this is the starting. বুঝতে পারলে স্টার্টারের ব্যাপারটা? Now we can have another sequence, another logic also. It can be based on the current sense. That means if you see here, the current is rising between remaining between IA1 and IA2. So I start with IA1 and wait till IA2 is reached, and then again, and I will again wait till IA2 is reached again. Again I will switch on. So this way also I can do it. So time is an approximate thing, but that switching through current will be more realistic, because I am allowing the current to rotate between this IA1 and IA2 based on sense. But here you require an additional sensor, current sensor. You require an additional sensor, current sensing unit. Or you can have speed sequence also. You can have speed sequence also. Now here I have written by mistake current sequence, but it is actually speed sequence is shown, speed sequence. Because speed also you see here, the speeds are rising, omega 1, omega 2, omega 3, omega 4, omega 5. Omega 5 is the end speed or rotary speed. So I can wait till my speed omega 1 is reached, then omega 2 is reached, like that. So this based on stop button 0, this will go. Now 0 is on. Now I am this is a instruction for fetching data from analog module, pull data, pull. So pull speed, maybe armature current, maybe speed. So it is written sometimes armature current, armature speed. So it's a prepared time back, so I did not have the time to correct. But anyway, you can understand easily. So pull speed, that means the input, speed input in the register where we are taking, we are fetching that data, and then compare with omega 1, right? the desirable speed, omega 1. When it is equal, the C1 will be 1, right? Now again, C0 is here, and I am pulling the speed, and I am comparing with omega 2. So then C2 will be 1. Then in the next rung, I will compare with omega 3, and so on. So either current or speed. So I can have, instead of speed, I can fetch from current, armature current, and compare with IA2 and then C1, armature current and compare with IA2 and C1, like that. So then for the current, actually you cannot have C0 everywhere. The first sequence you have C0, second sequence it will be C1, because C1 will be on, then again it will be fetching the current, they comparing with the current IA2. Otherwise, what will happen at the same time, all these factors C1, C2, C4 will be on, because C0 is simultaneously on. But for omega 1, omega 2, there are different omegas, so there is no harm. You can either put C0 to all, or you can have C0, C1, C2 also for omega. This you remember. This is basic logic diagram. Okay. So this is programmable logic controller. So you can have, I think there are various say modules or companies you have seen. Either it is Siemens, or it is Rockwell Automation, or it is Mesa. There are various companies or various you can say houses which design this PLC, or even ABB, right? You will find in industries, those who will be joining industries like say steel plants, petroleum plants like HPCL, etc., or power plants even sometimes, or any process industries like say Reliance, or even core companies like L&T's, or this Siemens, ABB, etc., will be handling these things. But basic logic will remain the same, whatever be the. So you have to have the analytical ability to think how to design the program, or how to have the outcome what we read, right? So I think I will end up here. Now, model of the DC machine, I think I won't discuss, because these two pages, because you have already read. Because see, the model of the DC machine is nothing but, if you apply the dynamic equation, so Vt equal to RAIA, LA dt K phi omega, T is K phi IA, then T minus TL is J d omega dt plus B omega. I think this has been known to you. Now, based on which you can develop your closed loop block diagram for DC machine. This is the motor block diagram. Okay, Vt to omega, right? Vt to omega. Unfortunately, this lower part is missing. Lower part is missing. This one, I think. This one. This is in the next page I have shown. So this is Vt, and this is K phi omega. So Vt minus K phi omega will give you EB, right? Sorry, IARA plus LDIDT. So from previous equation, if you have Laplace transform this equation, you have Vt minus K phi omega is RAIA plus LA into SIA, right? If you take common IA, RA plus SA. So this is, if you divide by RA plus SLA, you get IA, current. Now if you multiply with KFI, you get torque, right? And if you difference between take difference between load electromagnetic torque and load torque, get this equation: T minus TL is J into S omega plus B omega, all in Laplace, right? So 1 by J plus B, you get omega, all in Laplace domain, of course. This will be capital. I have written as small, just I mean various literatures have but normally you will find capital. So this is omega S. So now omega into KFI will give you EB. So this is the model for DC machine. So now if you have a control model, you have a speed reference, and then a speed feedback, and then this from here I will discuss in the next day. Okay. So I have given you many instructions, and then from the next day I think we can cover a little more. Okay. So now I will request you that if you have any doubts about what we have discussed for today, you can just tell me within these 5 minutes. Because it's a remote mode of teaching, which I know people are prepare, but anyway, we don't have any other option. Repeatedly, I am telling. So if you have any difficulty, so you can please come back. কারোর কোনো বোঝা কোনো অসুবিধা হচ্ছে? হ্যালো হ্যালো,
নো স্যার, কোনো প্রবলেম নেই।
ঠিক আছে, বুঝতে পারছো মোটামুটি? আচ্ছা, আমাকে মনে করে রোল শিটটা কিন্তু আজকেই পাঠিয়ে দিও, হ্যাঁ? আর তাতে যদি একটু ইন্ডিকেট করতে পারো আজকে কারা কারা আছে, হ্যাঁ? আমি প্রথম দিনটা, পরের দিন থেকে আর দরকার হবে না, ঠিক আছে? আচ্ছা, ওকে, ঠিক আছে। তাহলে নেক্সট ডে কবে তোমাদের ক্লাস হবে? এই টাইমেই তো? নেক্সট থার্সডে 4:30, তাই করে দিই। এই থার্সডে না, আজকে কি বার? ওয়েডনেসডে। ওয়েডনেসডে, ঠিক আছে, ওকে।
স্যার আপনি বইয়ের নাম বলছিলেন, কোন রেফারেন্স বই?
ও আচ্ছা, বই অ্যাকচুয়ালি দেখো, পিএলসি অ্যাপ্লিকেশন ডাইরেক্টলি বইতে পাবে না, এমনি ড্রাইভ অ্যাপ্লিকেশন গুলো পাবে। হ্যাঁ, তুমি দেখতে পারো ওই জিকে দুবের বই, হ্যাঁ, অথবা এন কে দে, নিশিত কুমার দে, এই বই দেখতে পারো। হ্যাঁ, এখানে কিছু কিছু আছে। আর পিএলসি অ্যাপ্লিকেশনটা ডাইরেক্টলি খুব তুমি খুব বইতে পাবে না। যাই হোক, আমি যেগুলো দেখাচ্ছি সেগুলো দেখো। আর ইন্ডাস্ট্রিতে তো যারা যাবে তারা তো এমনি পাবে। আর কোশ্চেন মোটামুটি মানে দেখানোগুলো অনেকগুলো দেখাবো। যে কোশ্চেন মানে বলতে চাইছি যে নর্মাল যে ক্লাস, সেগুলো এর মধ্যেই থাকবে। হ্যাঁ, ঠিক আছে,
ওকে স্যার।
হ্যাঁ, ওকে, তাহলে আমি বেরিয়ে যাচ্ছি। হ্যাঁ,
ওকে
থ্যাংক
স্যার।
ইউ স্যার।